All right, so we're going to cover this. This is the first part of Unit 9, covering Chapter 22 on current and resistance. So the first one, we've got to kind of look at what current is. So if we connect two of these plates that have charge on them, called a capacitor. Basically, you charge two plates that are near each other. The plates become neutral when the charge moves between them. So those charges have to move. Okay, so the motion of charge through a material is called current. You've probably heard this word before. So current is just the charge moving. And as this capacitor, or even as a battery discharges, the connecting wire gets warmer because some of that energy that's due to the charges moving transforms into heat energy in the wire. So the current is the charge moving through something. So when something discharges, so when something charges through, the wires get hot, but the current moves through. The current is moving through this light bulb. So like when you connect something to either side of a battery, you allow a spot for the charge to move, and that's your current. Interesting thing about this is this also is able to deflect a compass, which means there's some magnetic features to it. So the charge that moves is kind of a charge carrier to the charge carrier through your conductors. In metals, the charge carriers are the electrons. The electrons carry the charge from one place to another one. So these electrons are free to move through basically the surface of the material. So these insulators do not have free charges and don't carry a current. So this current is all about the charge moving. So when we apply some kind of electric field, the field exerts a force on the electrons, and the electrons begin to move. Now, they don't necessarily go in a straight line. They want to, but they run into all the other electrons that are trying to move. Unless if the only way the electrons move through something is if they have a force to push them through. Okay, so they have to have something to cause them to move. They just don't move on their own. They have to have something to cause them to want to move. But the fact that they don't always go in a straight line because they hit other things is called the electron's drift velocity. It actually makes them go slower than essentially the speed of light. So the collisions reset the motion of the electrons. So then it wants to go in a straight line. So these electrons go in all sorts of directions when they start hitting things. They want to go in a straight line, but they keep running into things that cause them to move in different directions. So in a plate capacitor, or even kind of like a little battery that's moving charge, the separation of that charge creates what's called a potential difference. Potential difference is that potential for the charge to move. If you kind of think of it like gravitational potential. The higher your gravitational potential, the higher you up, the more likely you are to fall. The separation between the positive and negative charges creates what's called an increased potential difference, a potential for that charge to want to move from one spot to the other one. You see that in a battery, it's your voltage rating. Like a 9-volt battery, one side has a lot of potential, the other one doesn't have a whole lot of potential because the charges want to move from one side where there's lots of potential to where there's no potential. And that potential difference creates the field that drives where the current is going to go. It wants to go from where there's lots of charge to where there's lots of potential to where there's no potential, ultimately evening it out. So we have this where the charges move. Okay, so the electrons are going to move from where there's a lot to where there's none. Conventional current right now is looking at the move of positive charges. So there's high potential for these positive charges to want to move down here. When there finally becomes a point where there's equal number of positive and negative charges all the way through, you have no more current. It doesn't move anymore. So the current at point B, the current is the same all the way through a circuit like this. If there's one path for the charge to move through, like in this picture, the electrons are flowing in one direction. The current is the same whether it's here, 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 or here. The current is all the same. And so your movement of charge is all the same. So the number of electrons isn't changed. Some of the energy is changed from electric energy to heat energy and light energy, but the number of electrons doesn't change. And this last statement is very, very important. Every electron entering the bulb is matched by an electron leaving the light bulb. So the number, if you think about it, the number of electrons at one given point actually never changes. It's just replaced by one and pushes the old one out. So the number of electrons in this whole system never changes. It's just the location of some of them. Okay. So think of it kind of like water. That water is going to move through and push things around. The flow of electrons does the same thing. The electrons move through, and like a water moving by a water wheel making it spin, the electrons flow through the light bulb, lighting it up. Okay, and the energy, so like energy is dissipated on this fan to different things. Energy from the electrons is dissipated on the light bulb up in this filament. It gets hotter and brighter. So law of conservation of current is that the current is the same at all points in a current carrying wire. So we have these two light bulbs. Okay, these are two identical light bulbs on this circuit that's been created that has current moving through it. So we're going to look at the brightness of these two bulbs. So current is conserved, so that means that anywhere through this the current is the same. So that means the current through these two light bulbs are equal, which means so the brightness of the bulb is proportional to the current. So identical bulbs carrying equal current have the same brightness. So they have the same amount of current moving through them. They're going to be the same brightness level. So the result makes sense in that the terms of conservation of energy, so that no charge is used up, no charge is like dissipated. There's energy that's given off, but the amount of charges, the amount of electrons moving through them is the same. All right. So kind of looking at what current really is. So a capacitor or a battery, a capacitor is a faster releasing form of energy than a battery. All right. So like we mentioned earlier, the convention of the current is the flow of positive charges. Okay. So the charge moves from area of high positive to low positive, or in case of the opposite, low negative to high or high negative to low negative. And ultimately, the charges will flow until there's no more potential difference. Current is really the rate of charge movement, or coulombs per second. Okay, so we're looking at really how many charges essentially pass by this given point right here. How many coulombs of charge pass through that given point? That's your current, which is I. I is your current. E is your electric field, making these electric charges move. So how many charges pass by a given point is your current. If you ever looked at water flow, it's how much water passes by a given point, okay, in a given amount of time. So current is number of charges divided by time, the rate of charge over time that passes a given point. So the current direction is from higher potential to lower potential, or the direction that the electric field is ultimately going. Current is measured in coulombs per second, which is actually abbreviated amperes. So 1 amp is 1 coulomb of charge passing by every second. Think back to the 1 electron is 1.6 times 10 to the negative 19 coulombs. That's a lot of electrons passing by a given second. Most of what your household appliances are typically about an amp. For a steady current, the total amount of charge delivered by a current I delivered through that time is Q equals I delta T. You can go look back to this, you rearrange and solve for Q. Q is I delta T. So 100 watt light bulb has a current of 0.83 amps. How much charge flows through it in a minute? So charge is current times time. We know our current, we know our time, and multiply them together, we get our number of charges. 50 coulombs of charge passes by that in a minute. Okay, but that's a lot of electrons that are flowing through it. So the Van de Graaff generator, several thousand volts, as you saw in class. So we have the discharge of electric eel can transfer a charge of 2 microcoulombs, MC is microcoulombs, in a time of, or millicoulombs, in a time of 2 milliseconds. What current in amps does this correspond to? So we have 2 millionth of a coulomb and 2 millionth of a second. So the current is 2 times 10 to the negative third current, or coulombs, is your charge. Your time is 2 times 10 to the negative third seconds. Okay, and your current then, we go back to current is charge divided by time. So 2 times 10 to the negative third divided by 2 times 10 to the negative third is 1 amp. Now, so that's the basic math for this, is current is charge divided by time. Now let's look at something called Kirchhoff's junction law. What this says is that all the current coming in to a given junction where either wires split or wires come together, the total current coming in has to equal the total current coming out. So in this case here, the current coming here has to equal the sum of these two. And same thing over here, the sum of these two coming in has to equal the current going out. So we have these currents here. So we have a 2 amp out, 3 amp in, 6 amp out, 4 amp in. We need to find the current going through this. So keep in mind, all the current going in needs to equal the current going out. Okay, so conservation of current, following Kirchhoff's law. So again, they have to balance the current coming in has to equal the current going out. So coming in so far, we have a 3 amp current and a 4 amp current. So we have 7 amps coming in. Going out, we have a 6 amp and a 2 amp current. So that's 2 amps going, or 8 amps going out. So to conserve current, so make the current all the same, the fifth wire has to have a 1 amp current going in. So 1 plus 3 plus 4 is 8. And then you have 8 in and 8 out, so your current balance is equal. Now that's the end of the first video. Make sure you answer the questions on the Google form, and if you have questions, please ask them on the bottom. We'll see you in class.